Greetings, welcome to lecture number 22 on basic circuit theory. I am Razavi. Today we'll spend some more time on RC circuit examples and try to hone our skills and improve our methods of analyzing these circuits as they become more complex or trickier and more interesting. But before we go there, let's take a look at what we covered in the previous lecture. We saw that there could be some driven circuits that also have initial conditions. And the question is, how do we go about analyzing such circuits? Well, one possibility is to start with the differential equation of the circuit, as we have seen in the past, and solve this differential equation with the non-zero initial conditions that we may have. So that's relatively standard, we can do that. But a more intuitive approach is to say that the initial conditions create their own response, and the input or the inputs also create their own response. So why don't we use superposition? So the idea is that for a given circuit, first we solve the circuit with the initial conditions present, but with all the independent inputs set to 0. Then we set the initial conditions to 0, and we find the response to the inputs. And then we add up the results, and that will give us the total response of the circuit to the initial conditions and the inputs. Now, one other example that we saw was this circuit where the capacitor and the resistor are located like so, and we are interested in the voltage across this resistor when the input is a step of height V1. And what we saw was that many interesting things happen in the circuit, and they all come from this equation. This equation says that if the current available to charge a capacitor is not infinite, the voltage on the capacitor cannot jump in 0 time. So before we apply the step, when the capacitor has a 0 volt drop on it, and after we apply the step, right afterward, the voltage across this capacitor cannot change. If the voltage across this capacitor cannot change and it's 0, it acts like a short circuit for a very brief amount of time. So during that time, right from 0 minus to 0 plus, the capacitor acts as a short circuit. So this voltage jump just goes right to the output, as we can see here. And then at the other extreme, when time goes to infinity, assuming that the current through the capacitor, the voltage on the capacitor becomes constant, that's our guess, because there are no other changes in the circuit beyond this step, then if the voltage on the capacitor becomes constant, the current through it becomes 0, so the device acts like an open circuit now. So when this device is an open circuit, there's nothing here, no current can flow through an open circuit, no current can flow through R1, the voltage across R1 has to be 0, and that's over here. So we see that we have the initial step, we have the final value, we can readily connect these and find the equation governing the behavior of the circuit. We also saw that the current flowing through this network, through this loop, is initially equal to this V1 over R1. Why? Well, again, because it's a short circuit at time 0 minus 0 plus. So whatever voltage we have here, we get here. We have a voltage of V1 right at this point. So V1 over R1 gives us that current. And then eventually, of course, the current goes to 0 because everything decays. So we end up with a 0 current, and we have an exponential decay. All right. So today we will look at another example that I started last time and didn't have time to finish. That's also a very interesting example. And before we go there, I wanted to refresh your memory that in a first order system, the response can be generally written as the response at time infinity plus the response at a 0 plus or 0 plus minus the response at infinity times the exponential of minus t over tau, where tau is the time constant of the system. Because the system is of first order, it is meaningful to define a time constant for it, as we have seen in the past. So I'm going to use this equation to solve this example that we started last time. Okay, So let's go back to that example and see what the circuit looks like. So here's the situation. I have an input voltage source, and it's a step. So we call it V1 U of t. So at time 0, it jumps from 0 to V1 volts. And then over here, we have a resistor, R1, and the capacitor, C1. So that's like our good old RC circuit, nothing strange here. But then we have another switch here that is originally open or not conducting. And then at some time t1, it closes or it begins to conduct. And that switch is connected to another resistor, R2. And we are interested in this voltage V out as a function of time. Okay? All right, so this is the circuit that we have. It has these two components in addition to the basic circuit that we have seen in the past. We just have to take our time and analyze it carefully. And first, of course, try to have some feel for what's happening before we jump into the equations. All right, so as usual, we will try to sketch the output as a function of time if we can, just to have a feel for what it looks like, so that when we write our equations, we can verify that our intuition is correct. So let's start from here. So I think I called this, I don't remember what I called it last time, maybe VA. So let's call this VA. This voltage, the voltage across this capacitor. We have a voltage here, which is V1 U of t. We have voltage here, VA with respect to this point. You can call this ground. And then we have a voltage here, V out. So if we were to sketch things, this is how we would imagine the output and input to be. So V in is a step, so it starts at 0 and jumps to V1 volts at time 0. Okay, so that's what we know. And then how about VA? So before this switch begins to conduct, before time t1, we just have our simple RC circuit responding to a step at the input. So we know how that goes, right? That's just an exponential that asymptotically approaches this value. So VA would have a behavior like this. So VA is 0 before we apply the step, right? There's nothing on the capacitor, that's our assumption, no initial condition. And then once the step arrives, this capacitor begins to charge towards this final value of V1. So VA wants to go like this with a destination of V1. Okay, so that's what we imagine that should happen. Now at some point at time t1, this switch closes, it turns on, and introduces this resistor into the network. All right, okay, so now let's try to sketch V out as well. All right, so V out as a function of time. Okay, 0 before time 0, nothing is going on in the circuit. In fact, V out is 0 all the way until T1, because while the switch is not conducting, there's no current through the resistor, there's no voltage across the resistor, so the output is 0. So if we mark this at time as T1, right here, then before T1, the main output is 0. All right? Now, at time t1, the switch turns on. It begins to conduct. What can we say about V out? And what can we say about VA? All right, so VA is the voltage across the capacitor. The voltage across the capacitor cannot jump in 0 time, cannot jump instantaneously if we do not have infinite current available. And here we don't have infinite current available, right? Any current going through this capacitor has to come through this resistor or that resistor, so it cannot be infinity. So if the current to the capacitor is not infinity, the voltage on the capacitor cannot jump. So this voltage, VA, which happens to be across C1, cannot jump right after this point, right? So this voltage has to still be here at T1 plus, just after the switch has turned on. Okay, so the voltage on the capacitor holds at this value for a little while, right? Okay, what can I say about V out? V out was 0 up to T1, and suddenly the switch turns on, and V out becomes equal to the voltage across the capacitor, because this is a short circuit, right? So we're sitting here, first we see 0, then the switch turns on, and now we are connected across the capacitor. So whatever the capacitor has, we see. And whatever the capacitor has, wants to keep. Doesn't change suddenly, right? So the voltage at the output will be equal to VA. So the voltage at the output jumps to this value. So let's call this value something. So we'll call this V2. So V out jumps to V2. Okay? The switch just turned on and introduced the voltage on the capacitor to the output. So the output jumps to V2. All right, and then what happens? Okay, so this switch is now a short circuit. I have a resistor here, a capacitor here, a resistor here. And these three have to fight it out to decide what the final voltage will be, right? If we wait long enough, all the currents become constant, all the voltages become constant, so we expect that the voltage on the capacitor will be constant. If the voltage on the capacitor is constant at time infinity, the current of the capacitor is 0, which means the capacitor acts as an open circuit. At time infinity, this is an open circuit, it's no longer there. How much is the output voltage? It's easy, right? It's the voltage divider between this and this. These two are dividing V1. So at time infinity, we can say both VA and V out approach a value, which is V1, the height of the step here, divided by these two resistors, because C1 is an open circuit at time infinity. So that would be R2 over R2 plus R1. This value holds for V out and for VA, because after all, now these are one node, because the wire has shorted them together, the switch. So this also eventually wants to reach a value of V1 R2 over R2 plus R1. So we have figured out some of the extreme cases, right? Right after time 0, 0 plus, 0 minus, right around T1 when the switch begins to conduct, and then at time infinity. Now how VA and V out go from wherever they are to this value, wherever they are to this value, you have to analyze and see, right? Is this value higher than this or lower? We don't know. So in other words, will this voltage go down to this value or will it go up to this value? We don't know, right? So those are things that we have to analyze one by one and figure out. But generally speaking, that's what we have. Okay? All right, so in a sense, you have to fill in the blanks here between this point and this point, and that's how we start to write our equations. All right, so let's begin to write the equation for VA before the switch conducts. So from here to here, that's easy enough. So I'm going to say for T less than T1, we can say that VA is equal to, the initial value is 0, the final value is V1, right? This is the voltage that VA wants to get to, but we don't let it because at this point the switch turns on. So before the switch turns on, we can say this is equal to V1, 1 minus x of minus t over tau 1. And if you want to put the u of t, that's okay too. So that is the voltage across the capacitor as we've seen in the past, right? You can see that at time 0, this is 1, this is 1, this is 0. At time infinity, this is 0 is equal to V1, and that's what we would expect to approach. So that's the voltage across the capacitor, VA, before the switch conducts. Okay, so how much is tau 1? Tau 1 is the time constant of the circuit. So we just have this and this, so it's just R1, C1. That's easy enough. And now we should analyze the circuit when the switch has turned on. So after t equals T1, what can we say? Well, we have to draw the circuit just to avoid any confusion with the switch replaced by a short circuit. So let's go ahead and do that. We see that our circuit looks like this. Now we have a resistor here, R1. Then we have a capacitor. Then we have a short circuit. And then we have R2. And we are interested in this voltage V out. And at this point in time, this is just equal to V1, right? It's a step that jumped from 0 to V1. So this is now V1, just constant, right? This is over here. Okay, so the only thing that's going on here is that the voltage on the capacitor at time T1, when the switch turns on, is not 0, right? It has some value, V2. So that becomes an initial condition for C2, or for C1. So C1 has this much voltage on it at this point in time, at T1. And from now on, the circuit has to work with this initial condition here and this constant voltage here and tell us what V out should be. All right, so let's try to find VA or V out. So VA is now equal to V out. Let's find these two at T1 when we make the switch over. So we say that VA of T1 is just that evaluated at T1, right? So we say V1 1 minus x pub minus T1 over tau. And that's what we call V2 here, right? We said at T1, VA has reached a value of V2. So we call this V2, okay? All right. So now we have a circuit. It's of first order. It has a bunch of things in it. It has, you can think of this as a battery. It has an initial condition here equal to this value. So let's write that here, V2. And it has an output, and we want to write the output as a function of time. Well, we can do that, right? Based on this equation. Because if we find the value at time infinity, we find the value at time is 0. Now we have to be careful about 0. And we have a time constant, plug these in here, we have everything, right? Okay, so let's do that very carefully. So I'm going to write y infinity, which is V out at time infinity, right? How much is that? How much is this voltage at time infinity? So here's the situation. I have a constant voltage of V1 that was provided by the step. I have an initial condition across the capacitor, and I let the circuit go, and I wait for a very long time. How much voltage will I measure here? But we calculated that, right? We said at time infinity, if the voltage on the capacitor is constant, the current through the capacitor is 0. It's an open circuit. So it's an open circuit here. We have only R1 and R2. They divide this voltage. So that would be V1 times R2 over R1 plus R2. Okay, so we have found the output at time infinity. All right, next we have to find the output at time 0. Now time 0 here has a special meaning for us. It's not really this 0, right? It's T1, because from T1 on, we have this circuit. So we say y at T1 is equal to the voltage at, for T1 plus, that's the initial condition that we need to plug in here. And we know this initial condition, that's this V2, right? So that's V2, and that's equal to V1 1 minus x pub minus T1 over tau. I hope it's not confusing all these voltages that we have. V1 is the height of the input step. V2 is the value of VA at time T1, this value here. Okay? And you don't have to call it V2, you can just keep the value for it like this, right? That's V1 times 1 minus the exponential, evaluated at time t1. Okay, so this is the value that we have initially just as the circuit begins to operate in this mode, right, with the switch conducting. Now with these, I should be able to find the time equation for V out, provided that I have the time constant of the circuit as well. I need this tau. Okay, so let's make sure that this is tau 1, so that we distinguish between these two. So we're going to call the time constant in this mode tau 2, because it might be different from tau 1, right? Tau 1 was only associated with this section because this section was out of the picture. But tau 2 is associated with the whole thing. So it's probably different, right? Okay, so how do we calculate tau 2? Well, we saw a method before. We said if you want to find the time constant in a circuit, it's meaningful only if it's a first order system, and there's a single capacitor somewhere. We're going to take the capacitor out and set all the independent sources to 0, and then find the resistance that this capacitor would see. And that's the resistance that gets multiplied by the capacitance to give us the time constant. All right, so we have the circuit. Let's go ahead and take the capacitor out and set all the independent sources to 0. Independent, which one is independent? Well, this one, right? This is an input. This input is set to 0. So the circuit now reduces to this. We have R1. The input is set to 0, becomes a short circuit. The capacitor is taken out. And we have another resistor here. And we are asking ourselves, how much resistance does the capacitor see if we sit here and measure the resistance between these two? Okay, this is easy enough. You see R1 between these two terminals in parallel with R2 between these two terminals. If you don't see it right away, you can draw it like this. Draw R1 vertically, R1, R2 also vertically. And we are interested in the resistance between these 2 points, right? So that would be R1 and R2 in parallel, not in series. Okay, so then I can say that tau 2 is equal to R1 in parallel with R2 times the capacitor that we have, C1. That's the time constant in this mode. Now I have the time constant, I have all these values. I can write the output as a function of time. So we say the out of t. This is for t greater than t1, right? Before t1, the circuit was different. So we have the value at infinity, which we found to be this much. So v1, the height of the step, times r2 over r1 plus r2, plus the value right after the switch turns on, which we call T1. V of T1 plus, that's this value. So V1, okay, we erased all of this. So that's V1, 1 minus x of minus T1 over tau 1. This is this voltage here, the voltage at the output, which it happens to be the voltage on the capacitor, right after the switch begins to conduct. Remember, this voltage cannot jump, so it has to be the value of the capacitor voltage before the switch turns on, right here. Okay, so that is this value minus y infinity minus V1 R2 over R2 plus R1, and then the whole thing times this exponential, x of minus t over tau 2. The time constant has changed, so it's tau 2, not tau 1. Tau 2 is this value, tau 1 is this value. Okay, very good. So that's what we observe. So we can try to plot this equation, but we guess that the shape of the output waveform somewhat depends on certain things. In particular, what we have to ask is, are we going down toward this value, or are we going up toward this value? In other words, how does V2 compare to this voltage? So we have to ask this question, and let's write it in a different color, because it's important. So we're going to write V2, which was how much? This one, right? So V2 is equal to V1, 1 minus exp minus T1 over tau 1. So that's the voltage that this capacitor holds at the moment that the switch begins to conduct. And the time at infinity is given by this. So we have to ask ourselves, which one of these conditions holds for this voltage right here and this voltage right here? So that voltage at time infinity is given by V1 R2 over R2 plus R1. Well, it depends on the values, right? It depends on how we choose T1. If T1 is relatively small, this voltage hasn't gone up much. So V2 will be lower than this final value. On the other hand, if T1 is relatively large compared to tau 1, then this voltage has gone up close to V1. It's gone up close to V1, so the final value, which is less than V1, will be less than this value. So depending on whether this condition holds or this condition holds, this voltage will be going like this to this value or going like this to this value, right? Depending on how far we have come in the initial charging process of C1. Okay, that's great. It doesn't cause any confusion, but the behavior of the circuit depends on the exact shape of this waveform, depends on how much voltage we have developed across the capacitor before the switch begins to conduct. All right, and we have to compare that with the final value that we have here. All right, so that's a nice example that brings together a bunch of concepts from what we have seen so far. We see that the time constant of circuit can actually change because we're switching things around. Some parts of the circuit are going out of the circuit or coming into the circuit. So certain things are changing. All right, let's see if there's anything else about this example that I wanted to mention. All right, that's all. Okay, so we're going to go to another example, which is also very interesting. And the final circuit is a little complex, so I have to take you through some steps of thinking and analysis before we get to that final circuit. Otherwise, it would be difficult to understand how the final circuit operates. And again, our emphasis here is try to understand the circuit intuitively. We want to feel what the circuit does rather than just jump into the equations and write them out. Sure, we can always write equations, but if we don't understand what the circuit is doing, the equations don't tell us much. There is interest in the ability to measure the pressure inside the eye, because that pressure is an indication of various ailments, various diseases that the eye may have. And in this paper, they deal with that. This is called a subcubic millimeter wireless implantable intraocular means within the eye, pressure monitor. So we want to measure the pressure inside the eye. All right, so of course, measuring the pressure itself is very challenging and very interesting, but we have a very simple and also challenging problem as well. So suppose I have some sort of device inside the eye that measures the pressure and then wants to convey that information wirelessly to the outside of the eye. Now, whatever device we have in there, some electronics, requires a battery, requires some sort of power supply. But we can't put a battery inside the eye. The battery will be too large. And eventually we'll run out of charge. So what do? How do we get power to inside the eye from outside without making any contact, without any wires? So that brings us to the concept of energy harvesting, which is a vast field for delivering energy without wires delivering energy wirelessly. And here's an example of how they do that. So the idea is as follows. We have a box outside that generates powerful radio waves. These radio waves propagate this way. Then inside the eye, we have a very, very small antenna. This is the symbol for that antenna that picks up the radio waves from outside. These radio waves have some energy, and they are converted by the antenna to a voltage. That voltage appears here. And now that voltage is applied to the circuit, which consists of a bunch of capacitors and some other devices that we haven't seen. These are called diodes, so that it eventually generates a constant voltage here, just like a battery. And that voltage is able to supply power to the electronics and allow the electronics to work, measure the eye pressure, and then transmit that information outside to the outside world so that we can have some information about the eye pressure. So what we see here is that the notion of picking up these radio waves by an antenna and then extracting energy, harvesting that energy from the radio waves by means of these capacitors and these diodes is extremely crucial for this type of application. This is an example of what we call energy harvesting. Isn't that beautiful? So let's go and go to the next page here and look at the next example. All right. Okay, so this example will have many parts, and the purpose of these parts is to help us grow our understanding of how the circuit comes about. So we're going to start with something very simple and just gradually make it more and more interesting. All right, in part A, we consider a circuit as simple as this. We have V in equal V1 U of t, a step, function applied to R1, C1. And we are interested in this voltage V out. Okay, we're also interested in this current. So we can call this something, we can call it I in maybe, the current going into the input of the circuit, right? Anything is fine. So we know, we have analyzed this very carefully before. So what we know is that V out, so maybe I'll try to write here, V out as a function of time. Again, the assumption is that the capacitor has a zero initial condition. So the capacitor begins to charge towards this final value of V1, right? So it's going to go like this towards V1. All right? And the current, I in, as a function of time, what does it look like? Okay, so it's 0 before time 0. When we apply this step, this voltage with respect to here jumps to V1, right? Okay, and this capacitor acts as a short circuit because there's not infinite current to charge it. So the voltage on the capacitor cannot jump, it has to stay at 0, so it's like a short circuit. So we see that this is 0, this is V1, so the current through R1 is V1 over R1. So the current through the capacitor through the entire loop jumps to V1 over R1, and then it decays to 0. At time infinity, all the voltages have stabilized, the current through the capacitor is 0, the current through the resistor is 0, so the entire current goes to 0. Okay, so that's something we know. Now, let's make things a little more interesting and start reducing the value of R1. All right, ultimately pushing R1 towards 0. So what happens? Okay, well, if R1 goes towards 0, let's change the color to red. We see that this response becomes faster and faster, right? So we say R1 is going down. Is that okay? And how about this one? Well, the initial current becomes larger because we have this entire voltage dropping across R1, so V1 over R1. If R1 is smaller, this initial current is larger. So what we have is this becomes taller, and it also decays faster. So again, that's for the case of R1 going down. So in the limit, when R1 goes towards 0, what should we see? Okay, so we say part B. So we have a step going to a capacitor. That's it. So V in is V1 U of t, C1, V out, and I in. Right? When R1 goes towards 0, this green circuit reduces to this red circuit. Okay, so can I quickly draw V out and I in for this red circuit? Sure. What I know is that V out is exactly the same as V in because they're connected by a wire. So we get this, and then we get this. V out jumps in 0 time and jumps to V1. And the current, I in, so this current is, you can imagine this becomes narrower and narrower and taller. So in the limit it becomes an impulse. So the current, as a function of time, becomes an impulse, right? So I in becomes an impulse. How much is that impulse? Well, it's easy to calculate, right? We can say that I in is equal to C1 dV out over dt. Right? The current going to the capacitor is equal to the derivative of the voltage times the capacitance, right? Okay. And the derivative of V1 U of t is V1 delta of t. So we have C1 V1 delta of t. So this impulse is given by C1 V1 delta of t. C1 V1 is the area under that impulse, right? The strength of the impulse is C1 V1. Okay, so one thing that we see here is that the voltage on the capacitor jumped in 0 time. That was possible because we could provide an infinite current. And that was possible because we have an ideal voltage source available to us. An ideal voltage source, by definition, delivers any current we want, including an infinite current. Of course, in practice, that's not possible, but we can come close to this scenario. Okay, so part A, part B. Now let's go to part C and twist the problem a little more. So let's go to part C and consider this situation. So I have V in is the same story, so V1 U of t. And this time, I would replace this capacitor by this series combination of 2 capacitors. So C1 and C2. Is that okay? Not a problem, right? Again, assuming they both have 0 initial conditions. So how much is I in this case? I in. Well, we just go back to previous equation and we say we just have to replace C1, this capacitor, with the equivalent capacitance of these 2. So we can say that I in is equal to C1 C2 over C1 plus C2 times V1 delta of t. Right? Remember that when capacitors are placed in series, the result is less than each of them. Right? So that's why we have this equation. Okay, so that is the current that flows through these capacitors. It's an impulse. When the voltage source jumps, it sees only capacitance, like here. And because it sees only capacitance, it has to deliver an infinite current so that the voltage on the capacitor can track the voltage of the voltage source. Right? You see that the output is the same as the input. For that to happen, we have to deliver infinite current to the capacitor for a very brief amount of time. All right, so one important result that comes from both of these is that we have charged the capacitor in 0 time, right? So let's just make a note here, because this becomes interesting later. So we charge C1 in 0 time, right? C1 had nothing on it over here, but suddenly it has this much voltage on it right after at 0 plus. So we managed to deliver a certain amount of charge to the capacitors in 0 time because we have an impulse of current available. All right, so in this circuit, which seems pretty trivial, I'm interested in another quantity that now becomes more interesting. And that quantity is this voltage. So let's go ahead and use this color here. I'm interested in the voltage across C2, so I'm calling this VC2, right? So I would like to plot VC2 as a function of time and then see how much VC2 is. So before time 0, there was no initial condition, VC2 was 0. After time 0, how much is the voltage on C2? We have the voltage across the whole thing. It's just that step, right? Like before. But how much is this voltage? It's probably not as much as this, right? You just have to figure out how much it is. All right, not a problem. We are looking for the voltage on a capacitor, and the only equation that we know that relates the voltage on a capacitor to current of a capacitor is the following. So we know that VC2 is equal to 1 over C2 integral of the current through the capacitance, right? And these 2 times have to be chosen properly. So let's just say 0 to t, and we have to figure out what these are. Right, that's the equation that we know for any capacitor that receives the current of I and generates the voltage VC2. All right, so let's go ahead and solve this. We have 1 over C2 integral of, how much is I? Well, we found the current. Because these 2 devices are in series, they carry the same current, right? That's one condition of being in series. So I in, which is this, is flowing through C2 as well. And that will be C1, C2, C1 plus C2 times V1 delta of t dt. And how about the integral limits? Well, we have an impulse, so we don't need to integrate all over the place. We can just go from 0 minus to 0 plus, right? From here to here. So 0 minus to 0 plus. Okay? So how much is this? You can see that this C1, this C2 cancels this one. Integral of delta is 1. And all that's left are V1 and C2 over C1 plus C2. So we have C1 over C1 plus C2 times V1. This is the voltage across C2 at time 0 plus. So what we observe is that the voltage on the second capacitor also jumps in 0 time, which is not very surprising, right? So VC2 also jumps at time 0, and its value is given by V1 times C1 over C1 plus C2. So let's digest this for a moment. That's an interesting result. So in summary, what has happened is that we apply the step here, like so. That step inevitably creates an impulse of current because it's facing a capacitor and nothing else. It's trying to change the voltage on the capacitor in 0 time, so it generates an impulse of current. That impulse of current flows through both of these capacitors, and it flows through C2. C2 says, I have an impulse of current, my voltage will change in 0 time. That's what it needs, right? So the voltage on C2 also jumps in 0 time and jumps to this new value. This value, of course, is less than this voltage jump, right? This is V1. This is less than V1, this amount. So then what would you call this circuit? You call the circuit a capacitive voltage divider instead of a resistive voltage divider. So that's a nice circuit to have. You can draw it like this, or you can draw it like this. C1 and C2. And what we see is that a step at the input from 0 to V1 gives a step at the output, but smaller, right? So that goes from 0 to V1 times C1 over C1 plus C2. So it looks like a resistive divider, right? It divides the voltage. It attenuates the voltage. But you have to be careful with what goes into the division factor. If we had resistors here, it would be R2 over R1 plus R2. But because we have capacitors, is C1, this one, not this one divided by the sum of the two. So we have to be careful about that. Okay, so far so good. I hope you're following everything nicely. What we see is that this little circuit acts as a voltage divider. Okay, maybe a big deal, maybe not. But we also see that it forces the voltage source to give us an impulse of current. All right, so if I had asked you right off the bat, how much is the time constant here, you would have said R1C1. How about here? Well, R1 is 0, the time constant is 0. How about here? Same thing, the time constant is 0. So in these cases, the time constant is 0. The circuit responds with 0 time constant. That's why we don't see any exponential behavior, right? We just see sudden jumps. And this current waveform that had an exponential tail has lost that tail. It has squeezed into just an impulse. So that's the result of having no resistance in series with these capacitors, and hence the nature of the circuit and the impulse that it generates. Okay, so that brings us to the next circuit, which would be also interesting to analyze, but our time is coming to an end. So I will follow this circuit with another one that is more interesting next time. We'll start with this capacitive divider and add a resistor here. And we'll see that adding that resistor suddenly changes everything. There will be some sort of time constant at some point, maybe not initially. And all sorts of interesting things happen once we have a resistor also added in parallel with C2. So that will be even more interesting circuit to analyze. I will see you next time.